Okay, so in this video we're going to show you how to do a digital simulation with Cadence. One thing I'm going to need all of you to do, and I'm going to email you to remind you this, is you need to let me know whether you have access to Cadence or whether you have access to a computer that you can install Cadence on. And I will send you a link for how to get a free student version of Cadence. Because we can do digital simulations with Cadence, which is something that you're going to need to be able to do for the rest of the term here. And so let's see what we can do here. So I'm basically going to show you how to do a digital simulation here. So first off, I just have a blank schematic open, nothing fancy about this. This is just a blank schematic. And I'm going to type in a little bit of text here first here. So we're basically going to have three inputs. And you know, just like we were doing in the labs before, you know, you would have to try using the dip switches all of these different settings, right? And I'm just typing them in right now. You'd have to try all of these different settings with the dip switch and create a truth table. Well, we can do the same thing here in our simulation, except instead of having to run 8 different simulations, we're only going to have to run one. Now, what I'm going to do here is I'm just going to create some kind of random circuit here. I mean, it's not really doing anything. I'm just going to go ahead, and you'll want to have this 7400 library installed. If you don't have it installed, again, how you can install libraries, you click on this little box that I did, and hopefully it just pops right up here. If not, you need to kind of go to the directory, and the directory would be Cadence SPB 17.2 tools capture library pSpice, and you would want to have the 7400 one, but I already have it installed. And then you can see here there's all of the basic chips we've been using in class, like there's the 74806, you know, we've got the 7408, so on and so on. So I'm just going to pick a couple gates here at random and just kind of put them together. I mean, it's not necessarily doing anything at all. I'm just picking some random gates here. And then I'm going to connect them up. So I'll connect that to there. This I'm just going to double click and put some lines out here. These are where the inputs are going to be connected to. And I'll wire that there. And then we need a line out here for the output, just so that we'll be able to put a probe on it. Alright, so now I've got my circuit wired up for the most part. I have to then create my digital inputs. And so in order to create my digital inputs, I go to the source menu. And if you've done simulations before, we've used to doing like things like VDC and everything else like that, but we're actually not going to use those. We're going to use something else instead called stimulation. This is a digital stimulation. Now, you can do 4-bit stimulation, which we will talk about maybe a little bit later, because you're going to have to do a 4-bit ALU, and you're going to have to build it from the logic level and everything from the gate level up on your project, but we'll talk about that at the end of the video here. But one that's easy to use, I think, is just the 1-bit stimulation. So I'm just going to put in 3 of them, because I got A, B, and C. And I'll just even call this, whoops, that's not where I want to go just yet. I'll just call this Stim A, Stim B, Stim C. And I'll just say that Stim C is connected to there, Stim B is connected up like this, and Stim A goes in like that. Just some random thing. Now, what we need to do is we need to configure and set up our stimulations to basically recreate this truth table. Now, if I think about it, I want to think about these in terms of columns. I want to get this to be 0, 1, 0, 1, 0, 1 for C. So I'm going to go and double click on C, and there's a bunch of commands, and the commands are how you can switch whether they are 1 or 0. So at 0 seconds, it's setting it to 0. Well, then I'm just going to say at 1 second, put it to 1. At 2 seconds, put it to 0. 3 seconds, put it to 1, so on and so on. And then ultimately here, we have now the 0, 1, 0, 1 going on. 0, 1, 0, 1, 0, 1, 0, 1. So that's stimulation C. Now if I look at stimulation B, it's 0, 0, 1, 1, 0, 0, 1, 1. So I do it for not every second, I do it every 2 seconds. So at 0, it's seconds, it's 0. Then at 2 seconds, I want to switch it to 1. 4 seconds, I want to switch it back to 0. And at 6 seconds, I want to switch it back to 1. Now, finally, for stimulation A, there's only one thing that we have to do, which is at 4 seconds, switch it to stimulation 1. All right, so we've got our circuit set up. We now need to set up the profile in order for it to simulate. Now, I've already been doing this, so I'm going to just here. Well, let me go ahead and create a new profile here. I'll call this new one here. I'm going to just call this digital 2 because I already have a digital 1. So digital 2. Now the first thing is you're going to have to change the runtime to an appropriate number. I'm going to have to run it for 8 seconds. And that's because at 0 seconds all the way up to 7 seconds is when I'm switching, but there's 8 possible values that I'm looking at, so I have to run it for 8 seconds. If you don't do that, it's not going to run correctly. The other thing is you want to go to options and look at the category, and it says analog simulation, but that's not what we're looking at right now. We want to do what's called gate level simulation. So I'm going to switch that to gate level simulation, and we're going to click on OK. And actually we're now ready to simulate. So I'm just going to go ahead and do the simulation button. Pulls my simulation up and it's done here. Now nothing's showing here because I haven't put any voltage probes down, but I can put a voltage probe down here, and if I put one down on stimulation A, for instance, we can see I get this 0 up to 1. Then if I go back and put another voltage probe here on B and C, we can see that what I wind up getting is my truth table: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, so on and so on. And let me scooch this in a little bit. You get the 1, 1, 1. Now the only remaining thing to do is to look at what the output is. And the output, well, as I said, I didn't really do anything spectacular for this. This is just some random one that I made up. Well, the output is 0 for every case except for this one right here. So, and that would correspond to 1, 1, 0. The output is 1, and then everything else, the output is 0. Now, I don't know about your eyes, but my eyes sometimes bug out on these a little bit. So sometimes, you know, you can zoom in. I haven't actually been able to figure out how to make this so that we can change the color or things like that. I'm sure there is a way, but I haven't been able to figure out how to do that or make it bigger or space them out bigger. But you get used to looking at these. These are actually sometimes referred to what are called timing diagrams. And so you can kind of see we're using a timing diagram to simulate all the possible inputs and then look at the output. So I'd encourage you to go back and look at some of the labs that you've done previously and see if you could simulate those circuits as opposed to just drawing them in Cadence. See if you can simulate them, because the simulation is going to be an important part of the project that we're going to talk about now. So the project here is due at the end of the semester. I don't have a date yet. The requirements for this, and actually let me just delete this here. the requirements for this is going to be that you have to provide a detailed report, which I'll give you a little bit more detail on that later on. But that's going to be where you have to talk about the theory about a 4-bit ALU. You're going to have to talk about the gate theory, truth tables, also talk about your design, why you chose particular gates, like if you have K-maps for, reducing complexity of circuits, et cetera, et cetera. That's things you're going to have. And then also, that would be where you're simulating it. I am not expecting you to build these. Obviously, with the difficulty of not being able to be in the labs, it's kind of difficult to ask you to build these. But I do want us to try and be able to simulate them, which is why, again, I need you to let me know as soon as possible if you have access to a PC that can run Cadence on it. Now, you're going to design a 4-bit ALU with the following specifications. So you got two inputs, A and B, and then you got your output. And then S2, 1, and 0 are sometimes what's referred to as an opcode or an instruction code. So if there's 0, that means it's going to add the two things on the input. If it's 0, 0, 1, it's going to subtract on the input. And then 0, 1, 0, you're going to just make this one smaller. And then this would be one bigger. And then we have an ANDing and an ORing operation, a negation, and an exclusive OR. Now I went down here and did a couple examples here for the ANDing, just to you make sure this is what's referred to as bitwise ANDing. So if A, for instance, was 1, 1, 0, 0, and B was 0, 1, 0, 1, A and B would be 0, 1, 0, 0, because you look at each bit and AND them together. So 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 0 and 1 is 0. And then if you do OR, it's the same thing. You're doing a bitwise OR on it, and so you'd wind up with 1, 1, 0, 1, and then of course not A would just be 0, 0, 1, 1, and you could also put down what the exclusive OR would be. Now, there are a couple other things here, that there are some flags here that are status flags. Basically, Z is going to be set to 1 if F is 0, and then Z should be 0 in all other cases. If F is not 0, Z should be 1. And if you think about it, there's actually a pretty easy way to get that, but I'll let you figure that out. C is your carry or your borrow out, and that's again because if you think of you're doing 4-bit adding, you might have a 1 on that carry out. V though is if you get an overflow. And an overflow would be a situation like, for instance, 4-bit, we can go up to 0 to 15, right? But if we did, like 15 plus 15, you might say, oh, well, we just have a carry out going on there. But if you did 15 plus 15, that's 30. And the next bit up, 32, might have some issues with that. So you have to look into whether you are going to be doing a carry out or you're going to be giving an overflow status. And you might have both of those set. For instance, carry and overflow might both be 1 at the same time. Overflow basically means you can't compute the result. We have 4 bits coming in, but I only have 4 bits going out, meaning, I basically can't add anything that's sum is going to be bigger than 15. Even though I can input numbers up to 15, the sum, I can't get anything bigger than 15 on the output. So in those cases, you'd have overflows. So you'll have those status flag as well. So the other requirements for this is that it has to be a gate level design, meaning that you have to design it all the way down to the gates, like AND gates and OR gates, or NOR and AND, and et cetera, et cetera. You also have to have a power presentation with notes, because normally I'd have you guys present in groups on your design here, but instead you're going to create a PowerPoint of your design and hopefully your simulations, and then write down a set of notes on what you would be saying, basically a script of what you would be saying to the group of us, so that I can go ahead and grade those. I mean, yes, it's not going to be you speaking, but it's as best as we can do right now. And so that's going to be the project, and that's going to be a significant portion of the remainder of your grade at this point. Um, what I am going to do is I'm going to have you guys work in groups. So you need to let me know who you are planning on working with, and that way what I'll do is I'll set up some Blackboard groups so that you can collaborate through Blackboard if you want to, or if you want to use Google Docs, that's fine. But what you need to turn into me is not a Google Doc. It's got to be a Word document that you turn into me as far as your final report. Now, as far as the weekly labs, I'd still like to be able to do some weekly labs, um, although obviously you can't do them. So what we're going to do starting next week is I'm going to build some circuits that do some interesting things, and we'll go through them. We'll talk about it. I'll show you some videos of me building the circuits and measuring and testing them. And then you're going to have to write basically summaries on what it was that you learned from the video and what it was that, well, quite frankly, I was doing in the video. Okay? So we're going to look at that starting next week. All right. So that wraps me up of everything I think I need to talk to you about this week. As far as the lab reports that you have been working on before spring break, let's just have those due next Tuesday by noon. There will be several reports that are going to be turned in, so if you haven't turned it in yet, turn in the report on the 7-segment display. If somehow you didn't finish it on the 7-segment display, turn in what you had gotten done and write up a good explanation of what you had managed to accomplish. If you have any questions or concerns at this point, please email me. All right? Have a good rest of the day and expect to hear from me next week and see some more videos.